बोलिए आपके सारे बच्चे लोग एग्जाम में टॉप करेंगे।
साल वेस्ट कर दिया? डोंट वरी, आने वाले एग्जाम में आपकी मार्कशीट कुछ ऐसी दिखेगी। सिर्फ ये 4 चीजें फिक्स कर लो। सबसे पहले लेजीनेस को किक करो और फिक्स टाइम पे पढ़ने की आदत डालो। अगर मोटिवेशन लो है तो कोई बात नहीं, इजी सब्जेक्ट को पहले पढ़ो। अपने फोकस को मेंटेन रखने के लिए हर आधे घंटे में 5 मिनट का ब्रेक लो और हर 2 घंटे में 15 मिनट का ब्रेक लो। अगर पढ़ते वक्त नींद आए तो बार बार फोन उठाने के बजाय दिन में 1-2 पावर नैप्स लो। और हाँ, एग्जाम्स में आगे रहना है तो फंडा ट्यूब को सब्सक्राइब करो।
सिमंदरी का हो गया?
साइड है।
मतलब वो यूट्यूब पे भजन वो वीडियो लगा।
बोलो और कुछ, खिचड़ी बांटना। टेबल सब साथ में हाथ रखो। आजा सीनियर क्लासेस, सीनियर सर रुको लकी सर आने दो, लकी सर सब बाल्टी लिया जाओ बाल्टी ले लो सब जिसका हो गया चले जाओ पीछे चले जाओ
क्लास में नहीं जाना पीछे जाना
सब किया याद पूरा करो
Hey, monsters! Here's a fun general knowledge quiz, Science Edition. Let's go! What is the chemical symbol for gold? AU. Which gas do plants absorb from the atmosphere during photosynthesis? Carbon dioxide. Who is known as the father of modern physics? Albert Einstein. What is the chemical formula for water? H2O. Which planet is known as the red planet? Mars. What is the process by which plants make their own food using sunlight? Photosynthesis. Which gas makes up the majority of Earth's atmosphere? Nitrogen. Who is credited with discovering penicillin? Alexander Fleming. What is the smallest unit of matter? Atom. Which of the following is a noble gas? Helium. What is the chemical symbol for the element iron? Fe. What is the force that pulls all objects towards the center of the Earth? Gravity. Which element is the most abundant in the Earth's crust? Oxygen. Which part of the human body is responsible for pumping blood? Heart. What is the chemical symbol for the element oxygen? O. Which gas do plants release during photosynthesis? Oxygen. What is the process by which plants lose water vapor through their leaves? Transpiration. Which planet is the largest in our solar system? Jupiter. Who is known for formulating the laws of motion and universal gravitation? Isaac Newton. What is the chemical symbol for the element sodium? Na. Which gas is responsible for the ozone layer in Earth's atmosphere? Ozone. What is the main component of natural gas? Methane. Who is known for the discovery of the principles of genetics and the Punnett square? Gregor Mendel. What is the chemical symbol for the element hydrogen? H. Which planet is known for its prominent rings? Saturn. What is the SI unit of electric current? Ampere. Who is known for developing the theory of relativity? Albert Einstein. Which gas do humans primarily exhale when they breathe out? Carbon dioxide. Which gas is responsible for the greenhouse effect on Earth? Carbon dioxide. What is the chemical symbol for the element carbon? C. Which force opposes the relative motion of two surfaces in contact? Friction. What is the process by which water changes from a liquid to a gas at the surface of the Earth? Evaporation. Who is known for discovering the double helix structure of DNA? James Watson and Francis Crick. What is the chemical symbol for the element silicon? Si. Which planet is often referred to as Earth's sister planet due to its similar size and composition? Venus. What is the chemical symbol for the element nitrogen? N. Which subatomic particle carries a negative electric charge? Electron. What is the chemical symbol for the element chlorine? Cl. What is the chemical symbol for the element potassium? K. Who is considered the father of modern chemistry? Antoine Lavoisier.
Hi, you're on a rock, floating in space, surrounded by more rocks, and gas, and a bunch of nothing, mainly. Oh hey, look at that, the rocks are going around the gas. Hold on, what the heck is going on here? To understand, let's look at a little bit of physics. Wait, did I say a little bit? To find out what kind of magic this is, we'll have to go back in time. Okay, not that far. Stop. Yeah, that's perfect. This is Gravity Guy, but most people call him Isaac Newton. One important thing he said is that force equals mass times acceleration. Now, what do all these words even mean? Force is a push or pull on something in a certain direction. Mass tells you how much of something there is, and it's also a measure of inertia, but we'll get to that later. And acceleration is the derivative of velocity with respect to time, but that's too many big words for my taste, so let's just say it's how fast your velocity is changing. The key takeaway is that if you apply force to a fixed mass, you get a predictable amount of acceleration. If you know all the forces acting on a basketball midair, you can predict with 100% certainty if the ball will go in the hoop or your neighbor's windshield. Whoa, did an apple just fall on my head? Yes, Newton, it did. Yeah, that must have happened for a reason, said Newton, as he discovered that two masses attract one another, making the apple fall. Yes, even you, no matter how ugly you think you are, attract pretty much the whole universe at least a little bit. Hey, can you put that on paper? Yup, said Newton, who gave us the law of universal gravitation. In other words, how much do bodies pull on each other given their mass and distance times a constant. Bigger mass, bigger pull. Bigger distance, smaller pull. Actually, a lot smaller pull. You see, as the distance increases, the force gets smaller by the square. That, my friends, is the inverse square law. Gravity is also the reason why planets in our solar system orbit the sun. They got their initial velocity when the solar system formed out of spinning gas, and since there's nothing in space to stop them from moving, they'll keep moving. Hey, that's Newton's first law. The sun is so massive that the force of gravity keeps pulling the planets towards the sun, but the planets are fast enough to essentially fall towards the sun but miss it, and this goes on forever, creating a round orbit. Actually, that's kind of a lie. Most orbits are not perfectly round, but more egg-shaped, and Pluto's orbit is just a complete mess, but you get the idea. In this case, the gravity is what we call a centripetal force. One thing many people confuse is mass and weight, and no, they're not the same. Mass tells you how much of this blob there is, and weight is the force of gravity the blob would feel. To make things clear, your mass would be the same on the Earth and on the Moon, but the weight you would perceive is different because the Moon has a weaker gravitational pull, meaning a weaker force acting on your mass. So really, you're not overweight, you're just on the wrong planet. Alright, enough about Newton, let's break some stuff. If you ever dropped your phone, it might look like this. What the hell, ground? Why'd you do that? The answer is energy. You know, the thing kids have after eating gummy bears. Energy has the unit joule, and it's not like force. It doesn't have a direction, it's just a number that's kinda chilling there as a property of a thing. You see, there's two main kinds of energy, kinetic energy and potential energy. In plain English, energy of movement and stored energy due to some circumstance. For example, when you held your phone, it stored gravitational potential energy due to being held above the ground at a certain height. Once you dropped it, that potential energy was converted into kinetic energy as the phone fell. Then it smashed into the ground, and the phone absorbed some of the energy, making the screen go boom. Work is defined as force applied over distance. For example, if you lift an apple by 1 meter, you would have done about 1 joule of work. This happened by converting chemical energy stored in your body to gravitational potential energy stored in the apple. As you may have noticed, energy and work have the same unit joule, so they must be the same thing? No, energy is the total amount of work that a thing could possibly do, and work is just the stuff that actually happened and required energy. If you try to lift a weight that's too heavy for you, you'd feel like that took a bunch of work, right? Well, yes, but your feelings are invalid in the face of physics. Mathematically, no work has been done, because work is force applied over distance, and since you didn't move the weight at all, no distance means no work. The key thing to remember about energy is that it cannot be created or destroyed, only converted, aka the conservation of energy. Okay, but a car that's moving has kinetic energy. When the car stops, assuming the car doesn't smash into a wall, where does that energy go? When you apply the brakes, there's friction between the brakes and the wheels, causing the car to slow down and creating heat as a byproduct. That heat is then dissipated into the surrounding air, and that makes the molecules in the air move faster. Things that move have kinetic energy, so ultimately, the kinetic energy is transferred from the car to the air. With this knowledge, we can define that temperature is just the average kinetic energy of atoms in a system. You see, all atoms, not just molecules in the air, wiggle, like this. The faster they move, the hotter things get. That is temperature. All that talk about hot stuff, I think it's time we talk about thermodynamics. It tells us that jumping in lava is probably a bad idea, but more importantly, the absolute mess that is entropy. Literally, it tells you how much disorder there is in a system, indicating the number of possible states a system could be in. For example, get an ice cube, no, not that one, yeah, that's perfect, and put it in the sun. The sun will obliterate the ice cube and turn it into water. Looking at the structure of ice and water, we can see that ice is more neatly organized than water, which just kind of goes all over the place. Also, the water could look like this, or even this, but the ice will always look a little something like this. In total, the system went from low entropy to high entropy, meaning more disorder and more possible microstates. This trend applies to everything. The whole universe is on an unstoppable path to higher entropy. It's also the reason why time seems to only go forwards. Practically, entropy tells us that some forms of energy are more useful for doing work than others. Burn some gasoline and your car will move, spitting out heat and gas. That heat and gas is pretty much gasoline, just in the form of higher entropy. And as you can imagine, this stuff won't really make your car move, and the gas won't spontaneously turn back into liquid gasoline, meaning the form of gasoline with lower entropy is more useful for doing work. Okay, but if you put some water in the freezer, will it not decrease in entropy? Yes, But the fridge is not an isolated system and will heat up the room more than it will cool down the water, increasing the total entropy. Want to see some magic? Whoa, what just happened? Some electrons apparently moved through some wires and let there be light. What is going on here? Objects have a fancy something called a charge. It can be positive or negative, or if you have the same amount of both, an object is neutral. Electrons have a single negative charge. The flow of electrons is called electric current. To describe it, we use three parameters: current, voltage, and resistance. Current is the amount of electrons passing through a wire in a given amount of time. Voltage is what pushes the electrons to move, but simply put, it's a difference in electric potential, so you can imagine it as a slope that goes from high potential to low potential, where the flow of current goes downhill. And resistance is pretty self-explanatory. This is Coulomb's law. Wait a minute, this is just Newton's law of gravitation in disguise. This tells us that electric charges attract each other in a similar way masses do. Opposites want to cuddle, while like charges literally couldn't think of a more disgusting thing than to be with one another. These four equations explain pretty much all of electromagnetism, but don't be scared just because they look scary. I mean, yeah, they do, but it's simpler than it seems at first. The first one states that if there is an electric charge, there will be an electric field, or this big E, emerging from it. Add another and you have an electrostatic field. These lines tell us in which direction a charged particle would feel a force at any given point. The second one tells us the same for magnetic fields, and even though electric charges are cool and can be alone, magnetic poles are not. They're very lonely, and there will always be a north pole together with a south pole, and a single pole can never be alone. Okay, now here's where things get kinda freaky. You know how electric charges only act on other charges and magnets only affect other magnets? Well, that's only true if they're not moving. The third and fourth Maxwell equations tell us that a moving magnet creates an electric field and a moving charge or electric field creates a magnetic field. One consequence of this is that current can seemingly come out of nowhere by moving a magnet next to a conductor. The moving magnet creates an electric field which makes the electrons inside the conductor go crazy. That is called induction. In other words, electric and magnetic fields are so tightly linked that they are two parts of the same bigger thing. Let's say we have a charge. Since it doesn't move, it has a static electric field. If we accelerate the charge, there will be a magnetic field around it. That magnetic field interacts with the electric field, which again changes the magnetic field, and this is a sort of chain reaction that makes the electromagnetic field radiate outwards into space as an electromagnetic wave. Depending on the frequency, the human eye can actually see this. It's called light, but most of the spectrum is invisible to the human eye and is used for things such as Bluetooth, wireless charging, and confusing human apes into thinking magic is real. Hey, can we go back to the water and look at those molecules? Yeah, those. What are they made of? The molecules are made of atoms. Atoms are made of a core and some electrons. The core is made of protons and neutrons, both of which are made of quarks. They're strange yet charming from up top down to the bottom. Oh yeah, there's some more stuff, like for example the overweight brothers of the electron. All of this together makes up the Standard Model, which we believe to be the smallest things in the universe. At least that's the excuse we have for not knowing what quarks are made of. Fun fact, depending on the number of protons in the core, you get different elements. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are a little overweight and very unstable, so they fall apart into smaller atoms. That releases ionizing radiation. Not so fun fact, that stuff will kill you. If you have a large group of atoms, you can predict when half of those will have fallen apart. That's the half-life. Depending on how unstable an isotope is, it will survive a certain amount of time. Some don't want to live, some really don't want to live, but some will live far longer than you probably will. Oh yeah, did I mention that light is like the fastest thing in the universe? To be exact, 299,792,458 meters per second in a vacuum. That is pretty fast, said everyone. Also, light is a wave, said everyone. Why? If you shoot it through two teeny tiny slits, it creates a fancy pattern due to interference, which is just a wave thing. You see, when two waves cross, they can add up or cancel each other out. These gaps are the spots where they cancel each other out. So in this case, light behaves like a wave. Nah, screw that. Everything you know is wrong, said Albert Einstein, probably smoking crack after hearing about the photoelectric effect and discovering that light comes in tiny packets called photons. I sure hope that doesn't unravel a whole new area of physics. Anyway, he said, as he continued to casually drop an absolute bomb on the entire field of physics with his theory of relativity. He assumed the speed of light is constant because it arises from two other constants. He also assumed the laws of physics are the same for everyone, regardless if moving or at rest. Now think about it. If two people turn on a flashlight but one person is standing still while the other person is on a moving train, wouldn't the person standing still see the other person's light as going faster than the speed of light? The reality is, no, it would be the same as their own flashlight. That's impossible, except if time passes slower for that person from the perspective of this person. In other words, if the speed of light is constant, time must be relative. Also, gravity is not actually a force, sorry Newton, but rather a consequence of masses bending space-time. Einstein thought the universe is a mesh of space and time, and anything with a mass bends this fabric. Also, all objects move freely on a straight line when moving through space. Gravitation is simply the result of objects following these bent lines which appear straight to them. If you have a hard time understanding this, you can imagine two people on Earth walking in parallel straight lines. Now imagine one standing on the east coast and one on the west coast of the US. If they both walk north, eventually they'll meet at the North Pole. Because of the curvature of the Earth, they ended up at the same point even though they both walked straight relative to themselves. Oh yeah, by the way, energy and mass are kind of the same thing, he added, which explains why atom bombs are so freaking powerful. According to this formula, even just tiny atoms can release a humongous amount of energy by giving up just a fraction of their mass during fission. What is fission? It's the same thing Oppenheimer used to make this thing go boom. You see, there's two main ways to gain energy from changing nuclei, fission and fusion. Fission aims to split the nucleus of an atom into two or more smaller nuclei, which is most often achieved by blasting the core with neutrons. Fusion is the opposite, where you combine two smaller nuclei to get one bigger one. The energy came from something we call a mass defect, where the resulting nucleus is lighter than the starting nuclei. This missing mass is what was converted to energy during fusion. Fission and fusion are cool, but you gotta be careful or you might just blow up the planet. That totally didn't almost happen before. Multiple times. Hey, remember when Einstein said light is a particle? He accidentally discovered a whole new field of physics which he thought is just a giant hoax. Quantum mechanics. This stuff is crazy. Another German guy called Max Planck said, yes, Einstein, you're right. Light does come in tiny packets. Actually, all energy comes in tiny packets, or quanta. Want to know where an electron is inside an atom? It's here. And there, and everywhere at the same time, actually. That's a superposition. It's not in one state, it's in multiple states at once, at least until you measure it. Then it chooses one cozy spot to be in. Schrödinger gave us an equation that gives you a probabilistic model of where you can find it if you were to measure. You can imagine this as a cloud, and the denser it is, the more likely it is for an electron to be there. But still, where exactly it will end up once you measure it is random. Speaking of observing particles, they're also super sensitive about their private data. Look at these two images of a flying ball. In one, you can clearly see where the ball is, but not in which direction it's moving, and in the other, you can see where it's moving and approximately how fast, but not where exactly it is at the moment. That is essentially Heisenberg's uncertainty principle. You can never know both the exact position and the exact speed of a quantum particle at the same time. Okay, let's recap. A small thing can be a particle and a wave at the same time, and when we try to look at them, weird stuff happens. But you know what? It gets even weirder. Think back to the double slit experiment. We know that a light beam acts as a bunch of waves and we get interference. But here's the weird thing. Even if you send individual photons after sending enough of them and detecting where they end up, you get interference. Like, how can that be? What did a single particle interfere with? Well, we think it interfered with itself because it acted as a wave and went through both slits at the same time. That's a superposition. Okay, well, let's just measure which slit it goes through. Yeah, that's not gonna happen. Once you start measuring which slit the photon goes through, it stops acting like a wave and the interference pattern disappears, as every particle chooses just one of the slits to go through. Sounds kinda suspicious to me. Anyways, all this knowledge is gonna cost you one subscribe and a thumbs up. Thank you very much, and you can decide if maybe you'd want to tip with a comment, perhaps?
अभी जो 7 सीरीज टेस्ट चला था इसमें से लास्ट फाइनलिस्ट जो नाम बचा है उससे तुम लोग 6 जन। तो यानी कि जो जीतने वाला नेम प्लेट है वो तुम लोग 6 जन में से कोई एक। सीरीज के हिसाब से हमेशा टाइम कम होते गया थर्ड में ज़्यादा मिला। आज ये कौन सा है 7 फाइनल सीरीज टेस्ट का, यही है ना? तो अभी तुम लोगों को एक्साइटमेंट है कि टाइमिंग क्या है ना? गेस करो कितना हो सकता है? 10 मिनट। कितना टाइम बचा देगा? कितना टाइम बचा है? बैठो, कितना टाइम बचा है? बैठो, कितना टाइम बचा है? कितना टाइम बचा है? कितना टाइम बचा है? 33 मिनट्स। ओके, ये जो लास्ट सीरीज है इसमें आपको टाइम नहीं मिलेगा। यू हैव टोटल 0 मिनट्स एंड 0 सेकेंड्स। तुम्हारे पास जो बचा वाला जो वर्ल्ड का टाइमिंग है उसको तुम लोग यूज कर सकते हैं। ये टेस्ट को पूरा यूज करना है। जो तुम लोग अभी तक टाइम बचा के आए हर सीरीज में वो टाइमिंग को अभी यूज करना है। समझ आया? लेकिन इसमें एक और चीज़ है, तुम्हारे पास में टाइमिंग अगर ख़त्म हो गया तो तुम टाइम ले सकते हो, एक्सटेंड कर सकते हो, लेकिन अगर तुम 1 मिनट लोगे तो -2 तुम्हारा मार्क्स कटेगा। समझ आ गया? एक्स्ट्रा अगर अपना वर्ल्ड का टाइमिंग से अगर ज़्यादा लेते हो तो 1 मिनट अगर तुम लोगे तो 2 मार्क्स कटेगा तुम्हारा पेपर से, तुम्हारा ओवरऑल टोटल मार्क्स में से 2 मार्क्स कट जाएगा। ऐसे ही करते करते तुम्हारे ऊपर डिपेंड करता है कि कितना टाइम। समझ आ गया? गेम समझ आया? तो इसीलिए जो तुम्हारा वर्ल्ड का टाइमिंग है उसको यूज़ करो। एक्सटेंड हो गया रन से हम लोग खुद ही वहाँ से माइनस करेंगे, तुमको पता चलेगा। ठीक है? तो गेट रेडी, रेडी रेडी। चलो ऑल द बेस्ट, बढ़िया सर। चलो चलो शुरू करो, शुरू करो। जोर से
8 मिनट इससे ले रहा हुआ 4 मार्क्स दे रहा हूँ।
8 मिनट ये तुम्हें दे रहा है और ये तुम्हें से कितना दे रहे हो? 4 मार्क्स। ओके, तुमको हरीश का एग्जाम से अब तुम्हारा टोटल टाइम कितना है? 24। तुमको सिर्फ 14 मिनट्स में एग्जाम कंप्लीट करना। 2 मार्क्स दोनों पहले बोला 10 मिनट्स कटेगा तुमको, तब जाएगा उसको 1 मिनट। 24 है ना? 24 में से 10 कट जाएगा। 34 से काट देगा, तुम नहीं काटना ना, मैम काटेगा। ठीक है, 34 से 10 कटा, 24 मिनट्स तुम्हारे पास। तुम्हारे पास अभी टोटल 8 मिनट्स है एग्जाम कंप्लीट करने के। ठीक है, अब तुम्हारा एग्जाम में से जो भी तुम स्कोर करते हो उसमें से 4 मार्क्स इसको मिलेगा। समझ आ गया?
Wondered how math, which you might have hated throughout high school, came into existence? I'm sure you haven't.
No.
Perhaps in the minds of many of us, it remains a pile of frustrating equations waiting to be solved or complex formulas that need to be memorized.
A lot of boring math later.
Nevertheless, I will still take 8 minutes to explain the origins and development of the language that forms the foundation of all science and technology, the underlying structure of the universe, mathematics. The story of mathematics begins around 30,000 BC with the rise of human consciousness. The first and most basic need was counting. To survive, early humans had to track their prey, their herds, the seasons, and the days. This enabled them to predict the future and manage resources. Primitive people used the method of one-to-one correspondence, a stone, a notch, or a finger for every animal in a herd. Yes, they used mathematics for survival in its purest and most practical form. During this period, mathematics was less a mental tool and more a physical tracking system. Among the oldest concrete evidence from this era are notched bones found in Africa and Europe. For example, the organized markings on the approximately 40,000-year-old Lubombo bone, South Africa, and the 20,000-year-old Ishango bone, Congo, suggest that people were not only counting but also organizing those counts, perhaps engaging in groupings that resembled simple addition and multiplication. The groupings on the Ishango bone have even been linked to prime numbers, suggesting that the people of that time had a more sophisticated knowledge of rhythmic counting than we might assume. However, the biggest deficit in mathematics during this period was the absence of zero. Number concepts were strictly tied to concrete objects. The abstraction of nothingness, or the empty set, had not yet arrived. This limited mathematics. For a civilization to advance, abstract thought had to surpass concrete calculation. With the development of record-keeping skills, the need to represent larger and more complex numbers would arise. By the 4th millennium BC, the rise of complex civilizations in Mesopotamia and Egypt fundamentally changed the need for mathematics. They were no longer just counting sheep. They were using mathematics in state administration, tax collection, calendar creation, and colossal architectural projects. The Egyptians made particular progress in the field of geometry. The annual flooding of the Nile River necessitated accurately recalculating and redrawing the boundaries of agricultural land, requiring precise calculation of right angles and surface areas. Special artisans called rope stretchers, harpanodaptai, divided the land using simple yet effective geometric methods, such as the 3-4-5 triangle. The Rind papyrus and the Moscow papyrus show that the Egyptians possessed practical knowledge regarding fractions, area calculations, and even how to calculate the volume of a truncated pyramid.
What? What?
The approximate value of p used by the Egyptians was quite accurate, and these methods, developed through trial and error, made the construction of the Great Pyramids possible. Yet, Egyptian mathematics focused more on how than why. Why? They did not feel the need to prove their methods. The biggest breakthrough in the history of mathematics came from the Mesopotamian civilizations that developed between the Tigris and Euphrates rivers. The Babylonians began to view mathematics not only as a practical tool, but also as a theoretical discipline, integrating it with astronomy. The Babylonians developed the sexagesimal system. This base 60 system, which we still use today for hours, minutes, and angle measurements, meant that the value of each digit depended on its position. This was revolutionary. They could now represent an infinite number of quantities by changing the position of the same symbols without having to memorize hundreds of different symbols. The Plimpton 322 tablet is the most striking evidence of how advanced Babylonian mathematics was. Dating back to around 1800 BC, this tablet contains a systematic list of Pythagorean triples. This shows that the Babylonians knew the basic principles of geometry, number theory, and trigonometry 1,000 years before Pythagoras. However, Babylonian mathematics also had a flaw. Despite using a positional system, they did not use a definite symbol for zero in the place values. The third evolutionary leap in mathematics took place in ancient Greece. While previous civilizations based mathematics on practical calculation, the Greeks founded mathematics on the question of why. They moved beyond calculation and felt the need to prove knowledge. Thales of Miletus is credited with being the first to introduce deductive proof to mathematics. He showed that a theorem could be proven not by empirical observation, but by a chain of logic. Pythagoras' most famous discovery was his theorem concerning right triangles and its power to explain the order of the universe. However, the Pythagoreans faced their greatest challenge with the discovery of irrational numbers. This shattered their belief that the entire universe could be explained by whole numbers. This problem also demonstrated the vast potential scope of mathematics. Around 300 BC, in Alexandria, Euclid gathered this scattered Greek knowledge and authored the monumental work, The Elements. He demonstrated how all geometric knowledge could be derived logically. The Elements laid the foundation for the modern model of scientific proof and served as the standard textbook for Western education for thousands of years. Archimedes was a genius in mathematical physics and engineering. He approximated pi to its most accurate value, fractionally, up to that point. While mathematical progress stalled in the Western world with the collapse of the Roman Empire, the mathematical revolution shifted east, particularly to India, and subsequently the Islamic civilization. Beginning in the 5th century AD, Indian mathematicians solved the problem that the Babylonians and Greeks had not, the invention of zero. Mathematicians like Brahmagupta defined zero not just as a placeholder, but as a mathematical entity, a number that could be both added and subtracted. The combination of zero with the Hindu-Arabic numeral system created the modern positional decimal system. This system simplified calculations so fundamentally that it was revolutionary for the future of mathematics and formed the infrastructure for today's finance and commerce. This knowledge later reached its peak during the Islamic Golden Age. Arab mathematicians adopted and developed the Indian system. Al-Khwarizmi, with his work Al-Jabr, the origin of the word algebra, introduced this new system to the West and established algebra as an independent discipline. Algebra is the art of finding the unknown using the known. It laid the foundation for modern equations. Concepts like trigonometry, sine, cosine, and tangent were also developed and disseminated during this period. This knowledge found its way back to Europe through figures like Leonardo Fibonacci during the Middle Ages, setting the stage for the scientific revival of the Renaissance.
More feeling!
The final major leap in mathematics occurred in the 17th century with the independent invention of calculus, differential and integral calculus, by Isaac Newton and Gottfried Wilhelm Leibniz. Calculus is the mathematics of motion and change. It allows us to examine instantaneous rates of change, derivatives, the areas of curves, and accumulated changes, integrals. This tool became the indispensable language for explaining the laws of the physical universe, from gravity to electricity and magnetism. Without calculus, space travel or modern engineering would be unthinkable. The 19th and 20th centuries marked the modern theoretical age of mathematics. Gauss, Riemann, and Lobachevsky invented non-Euclidean geometries by rejecting Euclid's 2,000-year-old untouchable parallel postulate. Sorry, Euclid. Alan Turing's theoretical work laid the foundation for modern computer science. Every digital device we use today is based on mathematical logic derived from the Babylonian positional system, the Indian zero, and Newton's calculus. Mathematics, starting from those first notched bones built with abstract proofs, algebra, and infinitesimals, is a living, continuously evolving language that reflects and explains the universe itself. We are the inheritors who continue to write the most complex sentences in this language. That is why we should not hate it. Thank you for watching. I put a lot of effort into this video. Please subscribe.
सबको अपना अपना टाइमिंग याद है ना? तो दिमाग में से वही रखो कि तुम्हारा टाइम क्या है, वही ये गेम है। सोच लेना हर एक मिनट कीमती है। 1 मिनट में 2 मार्क्स कटेगा। और तुम लोग वॉल्ट में जिस जिसका टाइम है उस लोग यूज़ कर सकते हैं। शशि अपना टाइम को खरीदा है, सॉरी बेचा है, राइट? 5 मार्क्स के बदले। और बायर कौन है? हरीश।
क्या लिखा है सर यार, आगे स्लाइड हाँ बस एक लाइन, बस एक लाइन।
हरीश के पास है।
तो ये सेमीफाइनल राउंड है, राइट? सेमीफाइनल में क्वालिफाइड हो गए बहुत लोग। अब बारी तुम लोगों का है जो सेमीफाइनल में जाएंगे डायरेक्ट, बिना कोई भी कंटिन्यूस सीरीज एग्जाम लेके बिना, क्योंकि तुम लोग का एग्जाम चल रहा है। टाइम वेस्ट नहीं करेंगे और डायरेक्ट तुम लोग जाएंगे कहाँ में? कहाँ में? सेमीफाइनल। सेमीफाइनल कब है? सेमीफाइनल आज नहीं है, सेमीफाइनल कल है। कल सेमीफाइनल है। तुम लोग जितना लोग आए, और एक मैसेज आया था ना कौन कौन एलिमिनेट होगा, कौन कौन सेमीफाइनल में चलेगी और लोगों के साथ में तुम लोग का मैच है, यानी कि तुम लोग भी सेमीफाइनल में चलो। समझ आ गया? आज का गेम कैसा है? तो 7 सीरीज टेस्ट का जो सबसे बढ़िया गेम है वो ये है, आज तुम लोगों को चिट्स मिलेगा, ठीक है? कॉपी का ज़्यादा चिट्स का नहीं बात करता है, चिट्स मिलेगा। तुम लोग अपना हाथ से उठाएंगे और उसमें जिसका भी नाम रहेगा उसका टाइमिंग तुमको मिलेगा आज एग्जाम लिखने के। समझ आया? जैसा कि अगर तुम लोग को एग्जाम्पल के तौर पे अगर हर्ष का मिला, हर्ष का कब का टाइमिंग कितना था, कितना बोर्ड में था तुम्हारा? 33 मिनट्स तुमको मिल जाएगा डायरेक्ट एग्जाम लिखने का। समझ आ गया? इसमें जो बाइंग और जो सेलिंग वाला सिस्टम है वो यहाँ में भी है। तुम लोग चाहिए तो किसी और से अपना मार्क्स का बदली डील करके ले सकते हो, टाइम परचेज कर सकते हो। अब इसमें तुम लोग एक बोनस पॉइंट है, वो ये है कि इन चिट्स में टीचर्स का नाम भी है, इंक्लूडिंग मेरा भी, ठीक है? तो अगर तुम लोग को अभी अगर सपोज तुमको मिला नेहा मैम का नाम, तो तुमको मिलेगा टोटल 55 मिनट्स, ठीक है? और अगर तुमको अगर मिला लकी सर का नाम, तो तुमको मिलेगा 60 मिनट्स, ठीक है? और वही जगह तुमको अश्विनी मैम का नाम मिला तो तुमको डायरेक्ट हाँ नहीं हमको लगता है अश्विनी कल का मैक्सिमम अश्विनी का, ठीक है? इसका टाइमिंग था 54 मिनट्स, ठीक है? अश्विनी के पास 54 मिनट्स का टाइमिंग था। तो उसके हिसाब से अभी टाइमिंग हम बताता है कितना कितना होगा। तो अगर नेहा मैम का नाम आया तो तुम लोगों को डायरेक्ट मिलेगा 57 मिनट्स, ठीक है। ठीक है, 57। लकी सर का नाम आया 60 मिनट्स, ठीक है। और वही जगह में अश्विनी मैम का नाम आया तो मिलेगा 70 मिनट्स, ठीक है। और अगर तुम लोगों को अगर मेरा नाम आया दैट मीन्स तुम लोगों को टोटल 90 मिनट्स, ठीक है।
सचिन आपका नाम ही नहीं लेगा,
ठीक है। तो मेरा नाम आया तो तुम लोगों को मिलेगा 90 मिनट्स, मेरा नाम भी है। लास्ट में सारा चिट्स ओपन करके तुम लोगों को दिखा देंगे किस किसका नाम था कि नहीं। समझ आ गया? क्लियर है? तो एग्ज़ाम बहुत मज़ेदार होगा। और रही बात में तुम लोग इस चीज़ को ट्रेड कर सकते हो, ठीक है। दैट मीन्स अगर तुम लोग को 70 मिनट्स या 90 मिनट्स या 60 मिनट्स या 57 मिनट्स ऐसा टाइम पास वगैरह मिल जाता है या फिर ऐसा टाइम जो तुम्हारे लिए ज़्यादा है तो उसको सेल कर सकते हो अपना टाइम।
एग्जाम की बात कर सकते हैं,
एग्ज़ाम शुरू होने से पहले करना है। ट्रेड का अलग से हम टाइम बताएगा, उस टाइम में तुम लोग ट्रेड करेंगे। यानी कि जैसा अगर किसी को अगर मिला हरीश को नेगेटिव में है, ठीक है। अगर हरीश का मिला तो तुम लोग को -2 मिनट्स मिलेगा, तो तुम लोग दूसरा से परचेज करना पड़ेगा। और एक बात याद रखना, अगर टाइम खत्म हो गया और उसके बाद तुम टाइम यूज़ कर रहे हो तो 1 मिनट के लिए -2 मार्क्स कटेगा तुम्हारा। समझ आ गया? समझ आ गया। लेकिन एक यहाँ में एक और चीज़ है, तुम लोग का मार्क्स कटेगा तो है लेकिन यहाँ में इंक्रीज होने वाला सिस्टम नहीं है। तुम लोग समझ आ गया? दैट मीन्स तुम लोग को जो टाइम के बदले में जो तुम लोग दे देते ये वाला वो तुम लोग ये नहीं। समझ आ गया? समझ आ गया? क्लियर है? क्लियर है? क्लियर है सबको? टाइम को परचेज करना है, सेल करना है, कर सकते हैं। टाइम हम बताएगा उस टाइम।
सर कितना टाइम देने से कितना मार्क्स मिलेगा? अभी टाइम को बेच सकते करके आप बोले ना, जो
8 मिनट्स में अगर तुम 8 मिनट सेल करते हो तो तुम अपना 8 मिनट अगर तुम सेल करते हो तो अपना 4 मार्क्स उसको देगा। समझ आ गया? ठीक है। उसको चुपाऊंगा, दो चुपाऊंगा।
Atoms. Yes, even you. Atoms consist of a core and some electrons. The core is made of protons and neutrons, and depending on the number of protons, you get different elements. Water is made of hydrogen and oxygen. This is some sodium. I wonder what happens when you... Oopsie. Quantum mechanics tells us that this is not what atoms actually look like. They look more like this, but we'll get to that later. For now, just think of atoms as having multiple electron shells. The electrons in the outermost shell are called valence electrons. Most of chemistry is really just the behavior of these electrons. Every element is listed in the periodic table. All elements in the same column or group have the same number of valence electrons. For the main groups, the number of valence electrons is just the group number from 1 to 8. Except for helium. It's too small to have 8 electrons, it can only have 2, but still, it acts like a noble gas, so it's just kind of grouped in with those. Luckily, the transition metals also follow a nice pattern. That was a lie, it's kind of a mess, but that's not so important for now, so we'll get to that later. Elements with the same number of valence electrons tend to show similar behavior in chemical reactions. For example, the first group without hydrogen is called the alkali metals. Here's some things they have in common. They have one valence electron, they're shiny metals, they're kind of soft, and they do this sometimes. All elements in the same row or period have the same number of shells. This number increases from top to bottom. Also, the mass gets bigger from left to right as each element gains a proton, an electron, and some neutrons. Depending on the number of neutrons in the core, you get different isotopes of the same element, most of which are pretty unstable and fall apart, releasing ionizing radiation. Fun fact, that stuff will kill you. If an atom has the same amount of electrons as protons, it has no charge. If it has more, it has a negative charge, and if it has less, it has a positive charge. Charged atoms are called ions. Negative ions are anions, and positive ions are cations. The periodic table is also pretty much a dictionary, as every cell tells you the name and symbol of an element, the number of protons in the core, which is also the total number of electrons, and the atomic mass, which is the mass of neutrons and protons combined. The periodic table is roughly divided into 3 categories. Left of this line are the metals, right of it are the non-metals, which are mostly gases, and the line is called the semi-metals, which have properties that fall somewhere in between. 2 or more atoms bonded together form a molecule. If you have at least 2 different elements, you get a compound. Oh yeah, this is probably a good time to mention that compounds often behave completely differently than the elements they're made of. Like, put together an explosive metal and a toxic gas, and you get, of course, an even more table salt. You get table salt. There's many ways to write molecules, for example the molecular formula, where you just count the number of each atom in a molecule and write them as a subscript number next to the element symbol. But that has some problems. Look at these 2 molecules. They have the same molecular formula, but obviously they're not the same. They're isomers. Showing this difference is probably kind of important. It's the only thing that separates graphite from diamonds, because they're both just fancy versions of carbon, and I don't think anyone's gonna go, yes, this dusty black blob is indeed very expensive. One way to show the structure of an atom is the Lewis dot structure, which represents the valence electrons and bonds as dots and lines. This is also going to help us understand why atoms bond in the first place. You see, everything in the universe wants to get to a state of lower energy. That's why a ball on a hill will roll down by itself, because that decreases its potential energy. This trend also applies to atoms. The state of lowest potential energy is having a full outer shell of electrons, which is most often 8, or in the case of hydrogen and helium, 2. If you think back to the periodic table, you'll see that all noble gases already have a full outer shell, which is why they don't really want to react with anything. If 2 atoms don't have a full outer shell, but can achieve one by sharing electrons, they will naturally do so, the same way a ball will go downhill, as their combined energy would be lower than if they were separate. The sharing of electrons is called a covalent bond. These bonds are also caused by the positively charged nucleus of an atom tugging on electrons of another atom. The strength of this pull is called electronegativity. In the periodic table, the electronegativity increases from bottom left to the top right. Therefore, fluorine has the strongest pull. It's just unbelievably desperate for an electron. If the difference in electronegativity is bigger than about 1.7, you get an ionic bond. A good example is sodium chloride. Chlorine would do anything for an electron, while sodium has one too many and just kinda wants to get rid of it anyway. Perfect, they both say, forming an ionic bond, where sodium loses an electron and turns into a cation, and chlorine gains an electron and turns into an anion. That seems pretty important. You might want to remember it. The most common place you see ionic bonds is in salt. Yes, also table salt, but more generally, when metals and nonmetals bond, you get asalt, which is just a grid of ions. Speaking of metals, a pure metal forms metallic bonds. You can imagine this as a huge grid of positively charged nuclei which are surrounded by freely moving electrons. You see, in a metal grid, the valence electrons are kinda promiscuous, or as the nerds call it, delocalized. They can move freely in a giant playground of nuclei instead of being loyal to just one. This kind of bond is responsible for the properties of metals, like conducting electricity and heat, and also being malleable, as in being kind of bendy. Like, you can hammer on this stuff until it's the most deformed, unelegant, and ugly-looking piece of material ever known, and it will just limp along as if nothing ever happened. If the difference in electronegativity is lower than about 0.5, the electrons are shared pretty equally and you get a nonpolar covalent bond. If it's bigger than 0.5 but smaller than around 1.7, one of the elements is pulling on the electrons pretty hard. Not quite hard enough to completely steal an electron, but definitely hard enough to skew the electrons a bit, making it a polar covalent bond. An example is water. Oxygen has a very high electronegativity compared to hydrogen. As a result, it pulls the electrons of hydrogen so hard that they kind of belong to oxygen, giving it a partial negative charge and leaving hydrogen with a partial positive charge. The presence of 2 poles with opposite charge is called an electric dipole. all permanent dipole molecules can interact with each other, and really with anything that has a charge. As a result, the molecules will tug on each other and arrange themselves in a way that oppositely charged ends are next to each other. The forces acting between them are called intermolecular forces, or IMFs. A specific example is hydrogen bonds, where hydrogen bonds to something very electronegative like fluorine, oxygen, or nitrogen, creating strong dipoles that tug on each other. But even if molecules are not polar at all, there can be electrostatic forces acting between them. How? Electrons move around inside the atoms, and by pure chance, they can end up on one side of the atom, creating a momentary dipole, which influences other particles next to it to become a dipole as well. At least for a very short time, as the electrons keep moving and the dipole disappears. This is called the van der Waals forces. The polarity of water also explains why it's one of the most versatile solvents to exist. It can pull apart molecules by tugging on charges, and it keeps them apart by surrounding a particle with its oppositely charged end. Water cannot dissolve nonpolar molecules though. It's the reason why water and oil don't mix, since fat molecules are nonpolar while water is polar. Just remember the ancient saying, similia similibus solventur. Or in the language that's actually spoken, similar things will dissolve similar things. Fun fact, soap works because the molecules that it's made from, which are called surfactants, have a polar head and a nonpolar tail. This way, when in water, they can surround, for example, nonpolar fat molecules and form micelles, which, along with the water, transport the dirt particles away. These are the most important bonds and forces ranked by strength: ionic bonds, covalent bonds, metallic bonds, hydrogen bonds, and van der Waals forces. There are three main states of matter: solid, liquid, and gas. Solids are tightly packed in fixed structures, where the particles can only wiggle, unless, you smash them. In liquids, the particles can move freely but are still confined to a fixed volume, as the forces between them are still strong enough to keep them together, and the particles in gases have enough energy to just do whatever they want and fill up all the volume you give them. Knowing this, we can find two important words. Temperature is the average kinetic energy of particles in a system, or how much and how fast they move, and entropy is the amount of disorder. Substances tend to be solid at low temperature and or high pressure, which is a state of low entropy, as they're neatly organized and don't move that much, and gas at high temperature and or low pressure, where they move around like crazy, so it's a state of high entropy. Strong bonds, like ionic bonds, lead to high melting points, as they take a lot of energy and therefore a high temperature to break apart. That's why most salts are solid at room temperature, whereas water, which is only being held together by hydrogen bonds, is a liquid. Well, actually, there's another state called plasma, which is ionized gas and can exist at very high temperatures, such as in stars, or very high electric potential. The latter is used for neon lights. Gas is ionized in a tube with a very high voltage. Collisions of the ions with other particles makes their electrons move to a higher energy state. Once they fall back down, the difference in energy is released as light. The color of the light depends on the element that's used in the tube, as each element has different but fixed energy levels, and the difference between those determines the energy and therefore the frequency of the released light, which is what changes the color. All possible frequencies that an element can emit are called the emission spectrum. All matter can be divided into two categories: pure substances, which can consist of one element or one compound, and mixtures. Mixtures consist of at least two pure substances and can be homogeneous or heterogeneous. Homogeneous means the substances will mix evenly and the mixture looks the same everywhere, like salt and water, which is a solution. Heterogeneous mixtures look different depending on where you look. They have distinct regions made of separate substances. One example is sand and water, which is called a suspension. Okay, well, what about milk? That looks the same everywhere, so it must be homogeneous. No, milk is something we call a colloid, or more precisely, an emulsion. The difference between salt water and milk is that the solute doesn't fully dissolve in the solvent, meaning there are bigger particles than in a solution, but smaller particles than in a suspension. This allows the particles to stay evenly distributed but not fully dissolved, placing them somewhere between solutions and suspensions. Hey, remember sodium and water? What's going on there? Explosions are really just chemical reactions that release a lot of energy in a very short amount of time. Also, they expand, like, a lot. There's a couple types of chemical reactions: synthesis, decomposition, signal replacement, and double replacement. Here's an example for each one. They all happen mainly for one reason: to decrease energy and get to a more stable state. Chemical reactions happen in certain ratios. For example, to produce water molecules, you need twice the amount of hydrogen compared to oxygen. This is called stoichiometry. These ratios are based on the conservation of mass, which says that mass cannot be created or destroyed, only converted. Practically, when dealing with reaction equations, you have to make sure that there's the same amount of atoms on each side of the equation, and if not, balance it out element by element. As a rule of thumb, you should balance out the metals first, then the nonmetals, and then hydrogen and oxygen at the end. But it's really just trial and error until everything is balanced. Okay, but if you wanted to make this reaction happen in a lab, how would we know that we have exactly twice the amount of hydrogen compared to oxygen? You can't just take 10 grams of this and mix it with 20 grams of that, because the atoms don't weigh the same, so 10 grams of both contain a different amount of particles. What to do? Just look up the atomic mass of the reactants and take that amount in grams. You'll get exactly this amount of particles. That is 1 mole, which is just an amount of something, kind of like a dozen. In other words, we can interpret the reaction as 2 moles of this react with 1 mole of that, which we can easily measure. It's important to differentiate between physical and chemical changes, as reactions only take place in the latter. Physical change happens when the appearance changes but the substance does not. For example, hammering metal. A chemical change happens when the substances themselves change, and this is often accompanied by bubbles, a funky smell, or, you guessed it, explosions. All chemical reactions need activation energy to take place. Wood won't just spontaneously react with oxygen and start burning, or else, the planet would be on fire, but if you give it enough energy, it will. Catalysts reduce the activation energy needed for a reaction, which makes it happen easier and faster. And as a neat bonus, they don't even get used up during the reaction, so you can just reuse them. Because chemical reactions are changes in energy, it's quite useful to keep track of it. Enthalpy is, simply put, the internal energy or heat content of a system. If the total enthalpy of a reaction is lower at the end than at the beginning, heat was given off to the surroundings, which is an exothermic reaction. If it's the other way around, a reaction is endothermic. It's easy to see how exothermic reactions can be spontaneous. It's kind of like a ball on a hill. It will only start rolling if you push it a little bit, but then it will keep rolling on its own, just like wood keeps burning on its own. But in endothermic reactions, you have to keep putting in energy, like pushing a ball uphill. That doesn't just spontaneously happen, right? Well, yes, actually it does. To get the whole picture, we have to look at Gibbs free energy, which looks at the change of enthalpy, but also the entropy of a system, which is dependent on temperature. If this whole thing is less than 0, the reaction is exergonic or spontaneous because free energy was released. If it's bigger than 0, it's endergonic or not spontaneous because free energy was needed and absorbed. Here's where temperature and entropy come into play. Even if delta H is positive, so the reaction is endothermic, if the change in entropy is big enough, it can offset this and make the total free energy negative, which means the reaction is spontaneous. But this is strongly dependent on the temperature. For example, melting an ice cube is endothermic because it absorbs heat, but also it increases the entropy a lot, as neatly organized ice turns into water, which is just kind of a mess. So this can happen spontaneously, but only if the temperature is above 0. If it's below 0, the water will spontaneously freeze, which is exothermic. If it's exactly 0, then no reaction will take place spontaneously. In other words, if delta G is 0, we're at equilibrium. Chemical equilibriums exist when reversible reactions take place at the same speed in both directions, which means that even if reactions are taking place, the concentrations of both sides stay the same, and to someone watching from the outside, nothing seems to be happening. We often find chemical equilibriums in phase changes, but also acid-base chemistry. According to Brønsted-Lowry, an acid is a molecule that donates protons, while bases accept protons. A proton in this case is just a hydrogen ion. So, with this definition, a molecule with at least one hydrogen that it can throw away can be an acid, and anything that can pick it up can be a base. This also means that once they react, they turn into the conjugate opposite, as an acid that gave away a proton can now accept one back, which is what bases do. A molecule that can act as both an acid and a base is amphoteric, for example water. A strong acid will dissociate almost completely into its ionic form, giving off a lot of protons to the water and therefore creating lots of hydronium ions. A weak acid just won't dissociate nearly as much, giving us a lower concentration of hydronium ions. So, to measure the strength of an acid, we can measure the concentration of hydronium ions. This is called the pH. Mathematically, it's defined as the negative log of the hydronium concentration, which means one step on the scale is a 10 times change, and also, since it's a negative log, the higher the concentration, the lower the pH. For example, pure water is in a chemical equilibrium. There's exactly one hydronium ion for every 10 million water molecules. In other words, the concentration of hydronium is 1 over 10 million, or 1 times 10 to the negative 7. Taking the negative log of this gives us a pH of 7, which is considered neutral. Anything lower than 7 is acidic, and anything above is basic, unlike you. You can do the same thing with hydroxide ions and you will get the POH, which keeps track of basicity. Fun fact, the pH and POH will always add up to 14 because they counteract each other, so by knowing one, you know both. Now, if you have a strong base and a strong acid and you pour them together, no, they will not explode, they will neutralize by forming water along with the salt, which is neutral. For example, hydrochloride and sodium hydroxide will form water and table salt. Oh yeah, speaking of table salt, remember how it consists of ionic bonds because sodium transfers an electron to chlorine? Well, that is called a reduction-oxidation reaction, or redox. If sodium chloride forms out of its pure elements, the sodium gets oxidized as it loses an electron and the chlorine gets reduced as it gains an electron. Logically, sodium is the oxidant and chlorine is the reductant. Of course not, that would make sense, it's the other way around. More accurately, redox reactions are reactions that change the oxidation numbers of elements, which are kind of like imaginary charges. There's just a few rules you have to know to figure those out. Hydrogen is mostly +1. Oxygen is mostly -2. Halogens are mostly -1. Single elements are always 0, and the number of all atoms in a molecule always have to add up to the molecule's charge. So this would total 0, while single ions just have their charge as the oxidation number. For example, in sulfuric acid, we have 4 oxygens, which totals -8. We have 2 hydrogens, which brings the total to -6. And since the whole molecule is neutral, sulfur must have an oxidation number of +6. Just by looking at the oxidation numbers of reactants and products, you can deduce the flow of electrons, which gives you these equations. If redox reactions happen in acidic or basic solutions, you can balance out the charges with ions and fix the stoichiometry with water. Okay, now to this weird looking thing. I spared you from it because for describing electrons, this is very simple and this is not. But this is actually pretty wrong. Electrons don't orbit in circles. Here's how it actually works. All electrons inside an atom are described by 4 quantum numbers: n, l, ml, and ms. N corresponds to the shells, so all electrons with the same n are in the same shell. Within the shells, we have subshells with multiple orbitals, which are 3-dimensional regions in space where electrons could be. We know these exist thanks to Schrödinger's equation, which gives a probabilistic wave function. You can imagine it as a cloud, and the denser it is, the more likely an electron is to be there if we were to look for it. L describes the shape, and ml the orientation of orbitals in a subshell. There are 4 subshells called s, p, d, and f. If electrons have the same L, they're in the same subshell. If electrons have the same n, l, and ml, they are in the same orbital. Also, the number of orbitals increases by 2 for every bigger subshell, starting at just 1 for s. The last quantum number describes an intrinsic property of electrons called spin, which can have 2 values. Some guy named Pauli said 2 electrons can never have the exact same quantum numbers inside one atom. Since ms can only have 2 values, every orbital defined by n, l, and ml can hold a maximum of 2 electrons with opposite spin. Therefore, the s subshell can hold 2 electrons, the p subshell can hold 6, d can hold 10, and f can hold 14. Now, the quantum numbers restrain each other like this, which means that the first shell can only have an s subshell, the second can have an s and a p subshell, and so on. This means that the first shell can hold a total of 2 electrons, the second can hold 8, the third can hold 18, and generally the number of electrons a shell can hold follows the rule 2n squared, with n being the principal quantum number. The principal quantum number, and therefore the total number of shells, increases from top to bottom in the periodic table from 1 to 7. Every element has a different number of electrons that fill up these orbitals, and the different subshells and orbitals are filled in a specific order called the Aufbau principle. Just write down the subshells like this and draw diagonal lines from top right to bottom left. To get an electron configuration, just look up the number of electrons of the element in the periodic table and fill up the subshells in this order until there are no electrons left. This would be the electron configuration of sodium. You can also look up the next smallest noble gas and shorten it by just referring to its electron configuration as the base, because those shells are full and don't change for any bigger elements. This is also how you can figure out the valence electrons for transition metals. Just look up their electron configuration, ignore the full shells of the next smallest noble gas, and the remaining electrons are the valence electrons. Easy peasy. Anyways, all this knowledge is going to cost you 1 subscribe and a thumbs up. Thank you very much. Your comment is my delight, and I shall now guide you, fine person, to the exit where the next lesson is excitedly waiting for you.
Bohnen und Klee gehören zu den 18.000 Arten der Familie der Hülsenfrüchtler. Die meisten Arten dieser Familie, einschließlich dieser 3, sind als Stickstofffixierer bekannt. Sie erhöhen den Stickstoffgehalt im Boden, den Pflanzen zur Produktion von Proteinen benötigen, die sie zum Wachsen benötigen, sowie von Chlorophyll, das sie zur Photosynthese benötigen. Eine Möglichkeit, dies im Garten zu nutzen, besteht darin, Stickstofffixierer mit anderen Pflanzen zu pflanzen, die viel Stickstoff benötigen. Oder sie könnten eine stickstofffixierende Zwischenfrucht wie Klee anpflanzen, um im nächsten Jahr fruchtbaren Boden zu erhalten. Okay, das kann nützlich sein, aber erfüllt Stickstoffdünger nicht denselben Zweck, nur bequemer? Warum sich mit dieser Stickstofffixierung befassen? Um dies zu verstehen, müssen wir verstehen, wie Stickstofffixierung funktioniert, was wiederum erfordert, dass wir den umfassenderen Stickstoffkreislauf verstehen. Beginnen wir also mit dem Gesamtbild. Stickstoff macht 78% des Volumens der Erdatmosphäre aus. Der größte Teil dieses Stickstoffs liegt jedoch in Form von 2 stark miteinander verbundenen Stickstoffatomen vor, was nicht sehr reaktiv und für Pflanzen nutzlos ist. Damit Stickstoff für Pflanzen verfügbar wird, benötigen wir die Hilfe von Bakterien. Verschiedene Bakterienarten ernähren sich von atmosphärischem Stickstoff und scheiden Ammonium aus. Dieses wird von anderen Bakterienarten gefressen, die Nitrat ausscheiden, das wiederum von einer anderen Bakterienart gefressen wird, die Nitrat ausscheidet. Alle diese Stickstoffformen sind für Pflanzen verfügbar, insbesondere Nitrat, das für Pflanzen Pflanzen am einfachsten zu verwerten ist. Pflanzen können diesen Stickstoff direkt aufnehmen, wenn er sich in der Nähe ihrer Wurzeln befindet, aber am häufigsten sind sie auf Pilzfäden angewiesen, die sich an ihren Wurzeln anheften und ihnen Nährstoffe im Austausch für die Zucker- und Kohlenhydrate bringen, die die Pflanzenwurzeln ausscheiden. Abgestorbenes Pflanzenmaterial ist ebenfalls reich an Stickstoff und wird mit Hilfe von Würmern abtransportiert, deren Kot eine Delikatesse für nitrifizierende Bakterien ist. Stickstoff verlässt den Boden unter anderem, wenn die Ernte eingebracht wird, wenn er vom Wasser abtransportiert wird oder wenn er gasförmig wird und in die Atmosphäre zurückkehrt oder wenn dem Boden Sauerstoff fehlt, wachsen verschiedene anaerobe Bakterien, die Nitrate wieder in atmosphärischen Stickstoff umwandeln. Beachten Sie, dass diese Dinge nur mit losem Stickstoff im Boden passieren, nicht mit Stickstoff in Organismen. Okay, wir wissen also, dass der Stickstoffkreislauf stark vom Leben im Boden abhängt. Ohne sie wären die Pflanzen ziemlich traurig, aber Sie haben vielleicht bemerkt, wenn der Fixierungsprozess von Bakterien durchgeführt wird, wo passen dann stickstofffixierende Pflanzen ins Spiel? Ob Sie es glauben oder nicht, stickstofffixierende Pflanzen fixieren keinen Stickstoff. Stattdessen schaffen sie einen Lebensraum für die Bakterien, die dies tun. Die Wurzeln dieser Klebpflanze haben kleine Knötchen, die große Mengen an stickstofffixierenden Bakterien beherbergen. Das von diesen Bakterien erzeugte Ammonium wird langsam in den Boden freigesetzt, damit benachbarte Pflanzen und Mikroorganismen es nutzen können. Wenn die Pflanze stirbt, verteilen sich die Bakterien im Boden, was zu einer Fülle von bakteriellen Verbündeten für den Stickstoffbedarf zukünftiger Pflanzen führt. Wissen Sie, wie ich vorhin sagte, dass Wasser Stickstoff aus dem Boden abtransportieren kann? Dieser Stickstoff landet in Flüssen, die das Ökosystem stören können, indem sie es Algen ermöglichen, die Oberhand zu gewinnen. Denken Sie aber daran, dass dies nur mit losem Stickstoff im Boden geschieht und nicht mit Stickstoff, der in Organismen eingebettet ist. Und Dünger fügt reinen Stickstoff ohne die Organismen hinzu. Wenn es regnet, fließen also Unmengen davon ab und verschmutzen das Wasser. Lose Stickstoffmoleküle verflüchtigen sich zudem viel leichter und setzen dabei große Mengen Lachgas, ein starkes Treibhausgas, in die Atmosphäre frei. Das ist aber noch nicht alles. Solche Mengen an reinem Stickstoff reizen Regenwürmer, die dann absterben oder die Erde verlassen. Es stört die nützlichen Pilze an den Pflanzenwurzeln und verändert den pH-Wert des Bodens, sodass er für Bakterien unwirtlich wird. Kurz gesagt, er tötet den Boden ab. Wenn der Stickstoff verbraucht oder ausgewaschen ist, fehlen die Organismen, die den Pflanzen helfen könnten, mehr zu bekommen. Dann muss man also mehr düngen, was das Problem noch verschlimmert. Und diese Organismen haben noch viel mehr getan, als nur Stickstoff zu liefern. Die Wurzelpilze haben auch wichtige Mineralien für die Pflanzen an die Oberfläche gebracht. Und jetzt, wo die weg sind, muss auch Mineraldünger verwendet werden. Anstatt mit diesem sich selbst erhaltenden Netz von Organismen zu arbeiten, die Nährstoffe frei austauschen, müssen wir mehr Geld ausgeben, um Unmengen an Düngemitteln in tote Böden zu geben, was das Wasser vergiftet und zum Klimawandel beiträgt. Wenn man bedenkt, dass toter Boden nicht in der Lage ist, Pflanzen mit Nährstoffen zu versorgen, ist es kein Wunder, dass der Nährwert von Gemüse im Laufe des letzten Jahrhunderts stetig abgenommen hat. Gesunde Lebensmittel erfordern gesunden Boden. Wenn der Boden um Sie herum also reich und lebendig ist, versuchen Sie, ihn so zu erhalten. Wenn der Boden um Sie herum jedoch tot oder im Sterben liegt, wie bei den meisten von uns, können Stickstofffixierer dazu beitragen, etwas mehr Leben einzuhauchen, damit unsere kleinen Verbündeten unter unseren Füßen eines Tages zurückkehren.
Floating in space. Have you ever wondered how we got here? Well, about 4.5 billion years ago, the Earth was a big ball of flaming rocks, constantly bombarded by even more rocks from space. Fun fact, those rocks probably had some water inside them which has now turned into steam. Breaking news, the Earth is cooling down. Oh yeah, did I mention that? Whoops, everything's flooded. But hey, at least there's some cool stuff at the bottom, like hydrothermal vents, which are piping hot and filled with a bunch of chemicals that can make some very interesting stuff. Wait a minute, what the heck is going on here? Biology is the study of life, but really, it's just chemistry in disguise. I mean, you and I are basically just a big ball of molecules that can make funny sounds. Carbohydrates, lipids, proteins, and nucleic acids are some of the molecules that are fundamental to life. Carbohydrates give you quick energy, lipids store long-term energy and make membranes, proteins make up tissues, and nucleic acids make DNA. Also, to make all the chemical reactions possible, living beings have inside of them a bunch of enzymes. They're special proteins that act as catalysts, which just means they help chemical reactions speed up by either breaking down or combining one specific thing. For example, lactase breaks down lactose, the sugar found in milk. Okay, so enzymes make life possible by speeding up chemical reactions, but what even is life? Scientists don't really seem to agree, but obviously a cat is different from a rock. The cat can produce energy by metabolizing food, it can grow and develop, reproduce, and it responds to the environment, whereas the rock does not. Also, unlike rocks, every living thing on Earth is made of cells, of which there's two main categories, eukaryotes and prokaryotes. Eukaryotes have fancy organelles which are bound by membranes, like the nucleus inside of which is DNA. Prokaryotes have none of those organelles, and the DNA is just kinda chilling there, like freely floating around. This is why prokaryotes are just single-cell organisms like bacteria and archaea, whereas eukaryotes can form complex organisms like protists, fungi, plants, and animals. These are what's known as kingdoms, which is a taxonomic rank, so basically how we classify different living things and how they're related to one another. Because there are quite a few species of life on this planet, and naming them cat, dangerous cat, and water cat wouldn't really be all that helpful, we also give every species a unique and unambiguous scientific name consisting of the genus and the species. One thing every species has in common is homeostasis, aka keeping certain conditions in check so you don't die. If you feel warm, your body will sweat. If you're cold, your body will shiver. A cell does kind of the same thing, just that it balances out concentrations of certain chemicals. You see, enzymes, for example, only work in a very specific environment, let's say some specific pH value. If this changes too much, the enzymes will denature and won't work anymore. To counter this, the cell needs to constantly keep up this specific pH value, which is controlled by the concentration of acid and base molecules. Okay, but how does the cell do that? The secret lies in the cell membrane. You see, it's a semi-permeable phospholipid bilayer. Okay, that's way too many words. All it is two layers of these funky-looking molecules with a polar head and a non-polar tail. This allows small molecules like water and oxygen to slip right through, whereas larger particles like ions need special channels that can be opened or closed, which gives the cell control of what goes in and out. Naturally, particles move with the gradient, so from a place of high concentration to a place of low concentration. Or, in the case of water, it can also move to a place of high solute concentration, so for example, salt. Welcome to Biology Pro Tips Season 1. Tip of the day, do not drink too much salt water. There's a bunch of salt in salt water. In fact, more salt than inside of a cell, which means it will draw water from your cells and dehydrate you. Yeah, that's it. Have a great day. Anyway, the process of balancing out gradients is known as diffusion and happens automatically, but by using a little bit of energy, particles can actively be moved against the gradient. The energy comes from adenosine triphosphate, or ATP. To be exact, the highly energetic chemical bonds between the phosphate groups can be broken to obtain energy. This is kind of important, as in every organism and every cell needs to make ATP, for example, through cellular respiration, which happens in the mitochondria. Together with oxygen, glucose, so sugar, is turned into water, carbon dioxide, and ATP. This is nice, but it only works if you already have glucose. Humans are heterotrophs. They eat food inside of which is sugar, which is then broken down into glucose. Plants, on the other hand, are autotrophs. Simply put, they said, screw food, I'll just make my own glucose by staring at the sun. You see, plant cells have small organelles called chloroplasts, inside of which is chlorophyll, which absorbs red and blue light but reflects green light, which is why most plants look green. The absorbed energy from light is used to split water and make a special form of carbon dioxide, which can then be turned into glucose and oxygen. Okay, quick recap. Once you have glucose, either from food or photosynthesis, you can do cellular respiration to get energy in the form of ATP. Chemically, ATP is what's known as a nucleotide. It has a phosphate group, a 5-carbon sugar, and a nitrogenous base. You know what else is made of nucleotides? Deoxyribonucleic acid, or DNA. It consists of 2 strands of nucleotides with the sugar and phosphate groups, but the actually important part is the nitrogenous base, which comes in 4 flavors: adenine, thymine, cytosine, and guanine. These bases can form base pairs through hydrogen bonds, where adenine goes with thymine and cytosine goes with guanine. These bonds are what holds the 2 strands of DNA together. Okay, that's cool, I guess, but how the heck does that store genetic information? I'm glad you ask. A gene is a section of this DNA that codes for a special trait by carrying a certain sequence of base pairs, which is like a recipe for making a protein. Why proteins? Because they're really important. They transport molecules, act as enzymes, and determine the way you look. For example, the difference between brown and blue eyes is the amount of a pigment called melanin in the cells of the iris. The OCA2 gene codes for P protein, which we believe controls the amount of melanin in cells, meaning that the proteins made from this gene could be what determines your eye color. Pretty cool. There's just one issue. Your DNA and its information is in the nucleus, but proteins are made in organelles called the ribosomes. How do we get the information from A to B? The answer is RNA. It's kind of like DNA, just that it's most often a single strand. It uses ribose instead of deoxyribose, and instead of thymine, it uses uracil, which makes it less stable. But that's besides the point. Here's what RNA actually does. Let's say you want to make the protein coded for by this gene. An enzyme called RNA polymerase will split the DNA and make a strand of RNA with a complementary basis, essentially copying the information from the DNA to the RNA. This is called transcription. The new strand is called messenger RNA or mRNA because it carries this message out of the nucleus to a ribosome. Remember how I said that a gene is like a recipe for a protein? Well, on the mRNA, which carries the same base sequence as that gene, every group of 3 bases, which is called a codon, codes for a specific amino acid, which are the building blocks for proteins. These amino acids are carried by special molecules called transfer RNA or tRNA, which have a unique anticodon that can only attach to its matching codon on the mRNA. The job of the ribosome is to read over codons on the mRNA and attach the matching tRNA molecules, which then leave behind their amino acid. As the ribosome moves along the mRNA and attaches more tRNA, which happens a couple thousand times, the amino acids combine into a polypeptide chain, which is just a really long chain of amino acids that can be bunched up, creased, smacked, and folded into a protein. Okay, let's recap. A gene is copied onto mRNA, which is then used to build proteins by assembling a chain of amino acids, aka transcription and translation.
Welcome to Biology Pro Tips Season 2! If you want to decode a sequence of RNA, there is actually a chart for that. Yeah, that's all. Have a great day.
Oh yeah, did I mention that you have like a bunch of DNA? You have about 20,000 protein coding genes, each thousands to millions of bases long, and that only makes up around 1% of your entire DNA. The rest is just non-coding. Plus, almost every cell in your body contains your entire genetic code, but certain genes can be turned on and off depending on the cell, which is good because otherwise your brain cells might just start making stomach acid, which would not be good. Fun fact, if you were to stretch out the DNA of just one single cell, it would be about 2 meters long. Wait a minute, how does that fit into a microscopic cell? Well, if you were to look inside the nucleus, you wouldn't find the DNA just floating around like this, or even this. No, you would actually find lots of these worm-looking things. To be exact, DNA is coiled up around proteins called histones, which are then condensed into strands of chromatin, which are then coiled up even more to make tightly packed units of DNA called chromosomes, which kind of look like worms. Different sections on a chromosome carry different genes, and the entire human genome is split amongst 23 different chromosomes, although every body cell has 2 copies of every chromosome, one from the mother and one from the father. For most chromosomes, the 2 copies are said to be homologous, meaning that they carry the same genes in the same locations. However, the 2 versions of a gene can be different, so the mother's gene could code for brown eyes while the father's gene codes for blue eyes. These different versions of a gene are called alleles. For most of your genes, you have 2 alleles, one on each chromosome from either parent. These alleles can be dominant or recessive, which determines which of them is expressed. For example, brown eye color is a dominant trait, which is shown by an uppercase B, whereas blue is recessive, which is shown by a lowercase b. All this means is that if you have the dominant brown allele, you will have brown eyes, no matter what the second allele is. Only when there are 2 recessive alleles will it be expressed. With this knowledge, we can predict the future. Let's look at how this trait is inherited from parents to children. Both of these parents have brown eyes, but also have a recessive blue allele in their genotype. Every child receives 1 allele from each parent randomly, so these are the possible combinations for the children. Most combinations contain the dominant brown allele, so the child will have brown eyes. But there is a small chance that a child gets 2 recessive alleles and has blue eyes, even though both parents had brown eyes. You see, it's what's on the inside that counts. Alright, that's cool, but reality is not always so simple. Some genes are not fully dominant, but not fully recessive either, which means that the phenotype, so the appearance, appears to mix. Crossing a red and a white snapdragon, where red is dominant and white is recessive, gives you a pink phenotype, which is somewhere in between, aka intermediate inheritance. Or crossing a brown and a white cow, where both colors are dominant, could give you a spotted cow, so both phenotypes are expressed equally, aka codominance. Hey, remember how I said that almost all chromosomes are homologous? Well, there's one exception, the sex chromosomes. Females have 2 big X chromosomes, whereas males have 1 X and 1 smaller Y chromosome. These are partially homologous at the top, but since the Y chromosome is so small, it's missing genes that are present on the lower part of the X chromosome. These genes are called X-linked genes. If one of these genes is a recessive trait like colorblindness, males are stuck with that trait, whereas females probably have another dominant allele to override it. This is why most colorblind people are male. Now, for genes to even be passed on, the body has to make new cells which can inherit the genes. There's 2 main mechanisms: mitosis, which is how the body makes identical copies of body cells to grow and repair tissues, and meiosis, which is how the body makes gametes, so sperm and egg cells. Mitosis starts with a diploid cell, so a cell with 2 sets of chromosomes. These chromosomes consist of 1 chromatid, which has to be replicated for the new cell. After replication is when you see the familiar X shape consisting of 2 identical sister chromatids. These are split into 2 identical diploid cells with 2 sets of chromosomes consisting of 1 chromatid. Meiosis also starts with a diploid cell, but after replication, the chromosomes commingle and exchange genetic information in a process called crossing over. The cell is then split into two non-identical haploid cells. These have one set of chromosomes, but they still consist of two sister chromatids. These cells split again into four genetically different haploid cells, where each chromosome has one chromatid. Meiosis produces haploid cells so that when two gametes combine into a fertilized egg or zygote, it again has the correct number of chromosomes. This is cool, but cell division is only a tiny part of a cell's entire life cycle. Most of its time is actually spent in interphase, aka just chilling. All it does here is grow and replicate all of its DNA so that it actually has enough genetic material and size to divide in M phase. There's multiple checkpoints in the cell cycle which are controlled by proteins like p53 or cyclin to check if the cell is healthy and ready to reproduce. If a cell is not quite right, it's either fixed or it destroys itself, which is called apoptosis. Or at least, that's what it should do. Normal cells replicate until there's no need to, but some cells just keep going. This is because they don't respond correctly to these checkpoints and end up replicating out of control and functioning wrong, which is also known as cancer. This damaging behavior is often the result of a gene mutation, which is a change somewhere in the base sequence of a gene. This can happen during DNA replication when a single base is changed, left out, or inserted into the original sequence. This often changes the protein coded for by that gene, and let's just say that change is often not optimal. Another type of mutation happens in chromosomes, where entire sections of a chromosome could be duplicated, deleted, flipped around, or transferred between chromosomes. The most famous chromosomal mutation is probably when the 21st pair of chromosomes has an additional copy, so that there's 3 instead of 2. The result? Down syndrome. Mutations might seem like a bad thing, but actually they can also be neutral or even beneficial. For example, a species of yellow grasshoppers might mutate and become green, which makes them blend in with the grass and get eaten less. Over time, you can expect to see more and more green grasshoppers as their fitness has increased. Not that kind of fitness as in they can have more offspring because they get eaten less. This is natural selection and the driving factor behind evolution, as the poorly adapted species gets selected against and the fittest species, which has adapted to the environment, survives and has the most offspring, passing down the trait that made them survive. But sometimes random species get lucky and survive big extinction events or maybe find new land with no competition. They're gonna survive even if their genes are actually kinda bad. This is called genetic drift. If you think adaptation is cool, yeah, but it also kinda sucks. You see, humans can get sick from bacteria or viruses, but nowadays we have medicine that works. Good. However, what if the bacteria mutates and suddenly the medicine doesn't work anymore? Well, that's kind of exactly what's happening, and we have no clue how to fix it. So, yeah. Oh yeah, by the way, one thing many people confuse is bacteria and viruses, and no, they're not the same. Bacteria are prokaryotes, they consist of a single cell which can reproduce on its own, and we treat bacterial infections such as strep throat and tetanus with antibiotics. Viruses are not made of cells. In fact, we're not even sure they're alive. They share some signs of life, but they can only reproduce inside a host. They don't grow, so it's not really alive, but it's not dead either. It's more like a non-living kind of thing. Also, you cannot treat viral infections with antibiotics. Most of the time, you just have to chill out and let your immune system do its thing. Now you might think bacteria are a bad thing, but actually you have millions of good bacteria inside your gut. They live in symbiosis with you. You give them food and they help you digest it. Speaking of digestion, your body is made of many complex organ systems that work together to make sure you don't die. And I know what you're thinking. Actually, I don't, but I know how you're thinking. The nervous system, consisting of nerves which connect to the spinal cord and lead to your brain, is made of cells called neurons, which can conduct electricity along this long tube called the axon. Anything you see, think, and feel, it's all just electrical signals going to your brain, and your brain telling your body how to respond. To be exact, the signals are called action potentials and happen at the same strength and the same speed every time. So the only difference between, hey, I'm a little cold, and oh my god, I'm on fire, is where it happens and how frequent the signals are. When a neuron is just chilling, the axon is more negative on the inside than on the outside because there's an unbalanced amount of ions. This causes an electric potential of about negative 70 millivolts. When there's a stimulus, signaling molecules called neurotransmitters dock onto ion channels on the axon and open them, letting ions flow and changing the electric potential around that area. Now, action potentials are all or nothing. A small stimulus won't really do anything, but if the potential exceeds about negative 55 millivolts, the neuron gets excited. Ion channels around the stimulus open and ions rush into the cell. This causes the charge distribution in that section of the axon to reverse for a split second, which is called depolarization. Ion channels that are next to this area are influenced by this and open as well, which causes a chain reaction that sends the signal all the way down the axon. Some neurons have a myelin sheath made of Schwann cells, which insulate the axon and only leave tiny gaps called nodes of Ranvier. If there's a stimulus, the charges can jump across the nodes, which transmits the signal way faster than a normal neuron. But either way, at the bottom, the electric signal reaches a terminal button, which connects the current neuron to the dendrites of the next. If you were to zoom in, you'd notice that the two cells don't even touch. There's actually a small gap. This is once again where neurotransmitters come in. Once the button is depolarized, tiny packages of neurotransmitters get released and bind to receptors of the following dendrite, either blocking it from doing anything or causing another action potential which repeats the cycle. Something in my brain's telling me that you should definitely subscribe, and also if you want to stimulate your neurons and find out how math and differential equations are used in biology, a resource I can't recommend enough is Brilliant, which has thousands of interactive lessons for everything from basic math to advanced data analysis and programming. They use a hands-on approach so that instead of memorizing formulas for hours on end, you actually understand and remember what you're even learning. Not only that, but they have plenty of real-life applications that you can immediately apply the knowledge to, building your problem-solving skills along the way. For example, their scientific thinking course lets you interact with scientific principles and theories, from simple machines like gears and the physics behind playing snooker all the way to Einstein's special theory of relativity. Sounds cool if you ask me. The best part, you can try everything they have to offer for free.
Once upon a time, there lived a man in a small village. He was very worried about his son. His son was lazy and careless. He never worked. He just wandered here and there in the village all day long. One day, the man decided to teach his son a lesson. He called his son to him. He said gently, "Son, there is a watch kept inside the cupboard. Bring it to me." The boy went and opened the cupboard. He took out the watch and came back to his father. The father looked at the watch and then said, "Now take this watch to the market. Ask everyone you meet how much they think it is worth." The boy nodded and went to the market with the watch. He showed the watch to different people. One man said it was worth 500 rupees. Another said 1,000. Someone else said 800. Everyone gave a different price. Some people even gave the same price, but no one agreed completely. The boy came back home and said, "Father, everyone told me a different price for the watch. Some said 500, some said 800. And some said 1,000. The man smiled and said, "All right, put the watch back in the cupboard." The next day, the man called his son again. He asked him to bring the same watch. The boy brought it and gave it to his father. Then the father said, "Now go to the market again. This time, don't ask the price of the watch. Ask people the price of the time inside this watch." The boy was confused. He didn't understand what his father really meant. Still, he obeyed and went to the market again. He asked the people he met, "How much is the time inside this watch worth?" People looked at him strangely. Some laughed at him. Some told him to go away. Some said, "What a foolish question." The boy felt embarrassed and sad. Finally, he stopped at a small shop where an old man was working. The old shopkeeper was busy repairing watches. When the boy asked him the same question, the old man paused his work. He looked at the boy with a kind smile. He understood what the boy was trying to ask. He said softly, "Son, you cannot put a price on time. You can give millions of rupees, but you cannot buy back even 1 second of your life. That is why you must use your time wisely." The boy listened carefully. The old man continued, "Time has one bad thing and one good thing. The bad thing is it passes. The good thing is you can choose how to spend it. Everyone in this world has 24 hours in a day, the rich and the poor both. The difference is how they use those hours." The boy's eyes filled with understanding. Something changed inside him. He thanked the old man and went home quickly. He told his father everything that had happened in the market. The man smiled with pride and placed his hand on his son's shoulder. From that day on, the boy's life changed completely. He started working hard. He began using his time wisely. He stopped wasting his days wandering around. He understood the real value of every moment. Friends, time is free for everyone, but it is priceless. You cannot buy it, but you can use it. You cannot keep it, but you can spend it. Once it is gone, you can never get it back. So use your time wisely.
Did you know that just like humans, plants have an immune system? It helps them defend against parasites as diverse as fungi, bacteria, viruses, nematodes, and insects. Over 75 years ago, an American scientist called Harold Flor studied how plants defend against parasites. He discovered that for each resistance gene in the plant, there's a matching gene in the parasite. He called this the gene-for-gene model. Flor's work was hugely influential. It helped guide breeding disease resistance in pretty much every crop plant. Later, scientists found out that plants have an immune system to defend against invading parasites. Flor's disease resistance genes turned out to be sensors that can detect the parasite and initiate an effective immune response. More recently, scientists realized that the plant immune system is much more complex than Flor's model indicates. Disease resistance genes appear to work together in intricate networks to deliver a robust immune response. These immune networks enable plants to detect and resist parasites more effectively for several reasons. First, networks are more robust and can still function even when one of the components fails. Second, networks enable plants to mount an optimal immune response when the environmental conditions are changing. Finally, networks are more adaptable, allowing plants to evolve more rapidly to keep up with constantly evolving parasites. This view of plant immunity has implications for plant breeding. We lose so much food to disease. If we can better understand how immune systems work, we can make plants more resistant to disease and produce more food using less pesticide than we do today. From Flor's gene-for-gene model to today's systems view of plant immunity, a fundamental understanding of how plants fight parasites is vital. The study of plant immunity is just one example of how fundamental scientific knowledge can be applied to directly benefit society.